Section 29.6, multi-electron atoms. So we're now ready to consider what happens when we build up atoms heavier than hydrogen, which have more than one electron. The hydrogen atom is somewhat unique. Well, it is unique in the sense that in its ground state and its in neutral configuration it has only one electron, and so that electron does not interact with any other electrons. In all heavier atoms, once you have two or more electrons, they interact with one another, which complicates matters significantly. And so the energy structure for atoms that are heavier than hydrogen, that have more than one electron, now have an energy level structure that depends not only on N, but L. For example, in the N equals 2 level, we have two possibilities of L, 0 or 1. 0 would be the 2s state, and 1 would be the 2p state. But you'll notice they're at different energies, and in general, the energy goes up with increasing L. And I also want you to notice something peculiar here, and that is when we're filling up the N equals 3 state, we have the 3s state, which is L equals 0, the 3p state, which is L equals 1, and then we have the 3d state, where L of the electron in that particular state is in the 3d state with L equals 2. But notice that the 3d state energy is slightly higher than the 4s state, and that is basically owing to the increase in repulsion between the electrons with higher angular momentum compared with the 4s state, which has now lower energy. So here we have a situation where the N equals 3 state has one suborbital, the 3d state, which is actually higher in energy than the N equals 4 state. You'll recall for the hydrogen atom that the energy of the levels in hydrogen depended only on N. So normally the 4 state, the N equals 4 state, should have higher energy than the N equals 3 state. But when we consider the angular momentum of the individual electrons, we find out that the increase in energy as a function of L pushes the 3d state to be above the 4s state. We'll find out the implication of that shortly. Okay, so in summary then, the energy increases as L increases until the very maximum L state is allowed, and keep in mind the maximum L state is n minus 1 for any given value of n. As the energy increases, states with different n begin to alternate in energy. As I just said, the 3s and the 3p states have lower energy than the 4s, but the 3d is slightly higher. And so that will have implications on the filling of the elements in the periodic table and the nature of their chemical behavior as they line up in that table. In 1925, an Austrian physicist named Wolfgang Pauli hypothesized that two electrons in a quantum system cannot be in the same quantum state. Anytime you have more than one electron in an atom, those two electrons cannot be in the same identical state. And the identical state is basically characterized by the peculiar or specific combination of the four quantum numbers: n, the principal quantum number; L, the angular momentum; m, the projection of the angular momentum onto the z-axis; and m sub s, the projection of the electron spin angular momentum on the z-axis. So for a unique combination of N, L, M, and MS, only one electron can occupy an orbital with those particular numbers. And this is called the Pauli exclusion principle because it excludes the possibility of two electrons being in the same state. There are deeper quantum mechanical reasons behind this principle, but they're beyond the scope of this course. But as long as we recognize that no two electrons can be in the same orbit, meaning the same specific quantum numbers, then we can start building the periodic table. For example, the ground state of helium has two electrons because helium is element number 2. It has two protons in the nucleus, two electrons orbiting that nucleus. And the electrons have, in the ground state, they both have n equals 1 and L equals 0. And so the only quantum number that can cause them to differ is the spin quantum number, m sub s. And so the two electrons can coexist in that state provided that they are opposite spin, that they are spin up and spin down so that they have different projections of ms. This is allowed, but notice there's no more possibility in this orbital to put any more electrons. And so the filling of higher shells can take on more electrons because higher shells, for example the n equals 2 level, has not only n equals 2, L equals 0, which is the 2s state, but it can also put electrons in the n equals 2, L equals 1 state, which is the 2p state. And we'll find out how many slots it has for electrons in just a moment. So in 1867, the Russian chemist Dmitry Mendeleev was able to noticed that there was a periodicity to the chemical properties of elements, and he was able to arrange them based on their chemical properties into a table which we call the periodic table of the elements. That's his organizational scheme based on chemical behavior of the elements and similarities between certain elements that are associated to be in the certain family, the same family of chemical behavior. And so here's a brief schematic showing the possibilities for how many electrons can sit in these shells. We already mentioned that in the 1s state there's only 2 slots. Likewise, in the 2s state there's only 2 slots. In the n equals 2 state, it's n equals 2. In the 2s state, it's n equals 2, L equals 0. And so the only thing that can cause those electrons to differ is their spin quantum number projection onto the z-axis. On the other hand, in the 2p level, we have n equals 2, L equals 1, in which case we have 3 possible projections of L onto the z-axis. We have L equals 1, L equals 0, and L equals minus 1. And because for each one of those, we also have the possibility of a spin up and a spin down electron. For example, a spin up and a spin down electron can both reside in the L equals plus 1 state. Spin up and spin down can both coexist in the L equals 0 state, and they can both coexist in the L equals minus 1 state, which gives us a total of 6 possible slots for electrons in the 2p level. All of the p levels, for the same reasoning, have 6 slots. In the d level, we have, so since n equals 3 in this particular case, little l can be 2, 1, or 0. And in this particular case, for the 3D state, L is 2, which means that it can have projections onto the z-axis of 2, 1, 0, minus 1, and minus 2. 5 complete projection states, and 2 spin states for each of those projections, since we can have spin up and spin down. So there's a total of 10 possible levels to be filled, or 10 slots to be filled by electrons in any d state. And all d states are basically the same in that respect. For the 4f, we have even more possibilities for the electrons. So as we now build elements in the periodic table, we start with hydrogen, which has 1 electron, and we know that that electron in the ground state sits in the 1s state. The higher angular momentum states for n equals 2, 3, 4, and so on can hold more than 2 electrons. For each value of little l, there are 2l plus 1 values of the spin number m. The magnetic quantum number, which is the projection of L onto the z-axis, and for each of those we have 2 possible projections of m sub s. So for example, for a state with L equals 2, which would be a d state, there are 2l plus 1 possibilities for the projection of that onto the z-axis, which correspond to 2, 1, 0, minus 1, and minus 2. And then for each of those substates, there's also the possibility of electrons being spin up and spin down. So that's how we get the total of 10 states in the L equals 2. So right here then, taking into account all possibilities, including the spin quantum number projections, we see that for any value of little l, there are 2 times 2l plus 1 different states that are possible. And this is called, taken together, all of these states are called a subshell of the atom. So here would be the number of occupancies, or the number of states that electrons can reside in for the various quantum number combinations. For an s state, we only have 2, spin up and spin down. For the p state, we have 3 sub-L states, each of which has 2 electrons, spin up and spin down possibilities, and so it has 6 slots. The d state has 10 slots, and the f state has 14 slots as we fill them. Okay, so let's think about what happens then when we start filling the periodic table. Hydrogen is the atom that has just 1 electron, and the ground state is the 1s configuration. If we add 1 more electron, and 1 more proton for that matter, to make it the next element, helium, which has 2 protons and 2 electrons, it also is in the 1s state, but now it's a closed subshell because the 1s state is now filled. We have 2 electrons, 1 spin up and 1 spin down. Those are the first 2 elements then in the periodic table. When we then look to the atom lithium, it turns out it has chemical properties that are very similar to hydrogen. It has 3 electrons, and so the 3rd electron is then going to be put into the 2s state, which is the next available energy state. Likewise, beryllium, the neighbor to lithium, also has its last electron in the s state, but now it has 4 electrons total, 2 in the 1s state and 2 in the 2s state, and we therefore have another closed shell, or closed subshell. If we add 1 more electron and 1 more proton, we end up with the element boron, element number 5, and so its valence electron is in the 2p state. And then from boron all the way up to neon, including boron, carbon, nitrogen, oxygen, fluorine, and neon, those are simply elements that as we add protons and neutrons to increase the element number, protons and electrons, as we increase the element number by p, or the proton number, and the number of electrons to make that atom neutral, we explore all the atoms from boron to neon, and they fill up all of the sublevels in the 2p state. So then we get to neon, which represents at the end of this chain of these the end of these this string of atoms. Neon is now a closed shell nucleus because it has all of these states filled. We have the 2 1s electrons, the 2 2s electrons, and the 6 2p electrons to make element number 10, which is neon. And the fact that it's a closed shell creates a stable chemical element. Neon is a very stable element and does not react easily because it has these closed shells. And the chemical reactivity of elements really depends on the last or valence electron or valence electrons. And in this particular case, all the electrons are nice and snug in their beds in closed shells and are therefore non-reactive. However, when we add one more proton and one more electron to make the element sodium, we now have to put that in the 3s state, which is a single electron in the 3s state, which represents a chemically very active species because that electron is not part of a closed shell and therefore can interact much more easily with the outside world, giving sodium its chemical behavior. So as we continue filling up the elements, we see that the periodic table starts to emerge as we keep track of the chemical properties. Note, for example, that in this particular row right here, this is the n equals 2 row, where L equals 1 or 0. So we have this is the n equals 3 state. It has possible values of L equals 2, 1, or 0. For the 2 level, for the n equals 2 level, we have the 3s, for the L equals 0 level, we have the 3s state. For the L equals 1, we have the 3p state. And for the L equals 2, we have the 3d state. Now, what's interesting about the 3d state is that we earlier noticed that it has higher energy than the 4s state. So in truth, as we're filling that shell, the 3d electrons, the states that correspond to the 3d electrons, are actually the first row in this transition element part of the table. But before they fill up, the 4s state, which is lower in energy, first is the one to be filled with potassium and calcium, element number 19 and 20. Once the 4s state is filled, then we start filling the 3d state, and that's what gives the periodic table this interesting shape, where the 3d electrons are now sitting down in the n equals 4 row because they have a slightly higher energy than the 4s. And then the last elements in that particular row of the periodic table are these elements to the right, which are the ones that correspond to the filling of the 4p shell. Then, in similar fashion, the n equals 5 state, which begins with rubidium, first fills the 5s states, and then the 4d states, and then the 5p states, and so on. So, without going into great detail, the filling of the levels, the filling of the allowed levels in atoms as we move up the periodic table, give rise to chemical behaviors which we can associate in families. We can look at all of the elements that have similar chemical behavior and put them into a category, whether that's the alkali or the noble elements or the so anyway, the various columns represent the elements with similar chemical behavior, and we can understand how they are laid out in this table basically by looking at the filling of the quantum mechanical levels and associating those various states of closed shells or unclosed shells with various degrees of chemical behavior, which then causes them to end up on the periodic table in certain columns. Okay, so we then have the ability, and of course the topic is a lot deeper than this. This is kind of a quick survey, but quantum mechanics in describing the atom in terms of the Schrödinger equation and in recognizing the various quantum numbers that correspond to energy and angular momentum and spin orientation, we are able to build up the entire periodic table and understand why it has the shape it has and why chemical elements have the chemical behavior that they do. So this was a huge success for the early part of the development of quantum mechanics and the description of the hydrogen atom.